So today we will continue with more BeyondPlanck talks on foregrounds, and we will also look to the future. So on that note, I'm very pleased to welcome our first speaker, Masashi Hazumi, that's representing LiteBIRD, and will tell us about the latest news from LiteBIRD. So please, Masashi, go ahead and share your screen.
Let me start. First of all, I'd like to thank the organizers for giving me this opportunity. So I'm going to say a few words on LiteBIRD on behalf of the LiteBIRD Joint Study Group. I'm Masashi Hazumi, the PI of LiteBIRD. Okay, so first of all, LiteBIRD is JAXA's strategic L-class mission selected in May last year. LiteBIRD is a satellite for studies of B-mode polarization and inflation from cosmic background radiation detection. So JAXA's L-class is for flagship science missions with $300 million US cost cap. 3 missions in 10 years will be launched with JAXA's H2A or H3 rocket. After the CRISM mission, which is for recovery of Hitomi X-ray satellite, the first in the series will be MMX, Martian Moons Exploration, around 2025, and then LiteBIRD in late 2020s. So after this selection last year, JAXA held a kickoff symposium on LiteBIRD. Here are some photos during the symposium. So the CMB torch was passed from Planck to LiteBIRD at the symposium. So this is a torch. Of course, the imitation I borrowed from Hitoshi Murayama, who was the ex-director general of CAVI IPMU. According to him, he bought this with some like $10 at the San Francisco airport. Anyway, so I think it's quite appropriate to talk about LiteBIRD at this BeyondPlanck workshop because this torch was passed. Okay, now the LiteBIRD overview. After the launch, LiteBIRD will go to L2 for observations for 3 years around the Sun-Earth Lagrangian point, L2, and then it's going to carry out millimeter wave all-sky surveys with 15 bands between 34 to 448 gigahertz, with about the degree scale angular resolution from 70 to 20 arc minute, more or less. Well, yeah, actually, sorry, it says 20, but for 400 gigahertz, actually, it's a bit better. Sorry, I need to correct that. Mission is to achieve the total uncertainty on delta R, on R, tensor to scalar ratio, better than 0.001 with CMB B-mode observation. So there are 2 telescope systems, middle high frequency telescope or MHFT. Actually, it has 2 refractive telescopes, but I'm now talking about one system, and low frequency telescope, LFT. And each has the TS bolometer arrays, and that's cooled down to 100 millikelvin. And also the telescopes are also cooled down to 5 Kelvin. So for that cooling, which is one of the very important elements of the satellite, we have a chain of cooling systems starting from V groups for radiative cooling, as well as the active cooling with pulse tube coolers, Stirling coolers, Joule Thomson coolers, and ADRs. And I'm going to touch on the instrument a little bit more, but as I'm going to say later, one important and interesting instrument we have in front of the telescope is a polarization modulator, which is an important part of the system for the polarization measurement. So the total mass is around 2.6 ton, power is 3 kilowatt, and data size is almost 18 gigabytes per day. So the service module is more or less pretty conventional. And we are talking to the some of the leading companies for satellite missions in Japan right now. Okay, so probably one of the most important things is that the LiteBIRD has a clear goal and will achieve it. Clear goal is this, as I said already, to achieve this delta R better than 1 times 10 to minus 3. And that also, with the given the angular resolution, that gives us more than 5 sigma observation for each bump in case R is sizable, greater than 0.01. And of course, this is coming from science. And so here I just list the rationale. This gives us a large discovery potential in between this 0.05 to 0.05. And then it also gives us, ability to test the simplest and well-motivated so-called Starobinsky model. Indeed, in our current estimation, with foreground cleaning studies, we expect to achieve something like 0.6 times 10 to the minus 3 if you talk about statistical uncertainty after foreground cleaning. So that gives us a possibility to really detect the signals, assuming Starobinsky model. And that's demonstrated here in the right figure. So that's a really exciting possibility. This is just a comparison, between LiteBIRD and the Simons Observatory. And then you see this LiteBIRD has this great possibility to really detect the signal. And in case you don't see the signal, it's gonna give us a clean sweep of single field models with the characteristic field variation scale of inflaton potential greater than the Planck mass, so which has pretty important implication in our quest for the ultimate the physical laws. Why measure from space? Of course, because space offers a superb environment, and people who worked on Planck know that. And no statistical or systematic uncertainty due to atmosphere. And those who worked on Planck are not probably very much knowledgeable about atmosphere. Of course, if you work on both ground and the space, you know both. But as one of those who have been working on the measurements on ground, atmosphere is really a nuisance. And I can say that. So, and no limitation for the choice of observing bands, which is also important for us to achieve the very high level of the foreground cleaning, and no ground pickup in space. So as a rule of thumb, talking about statistical uncertainty, since we don't have any additional radiation from atmosphere, as a rule of thumb, 1,000 detectors in space gives a comparable result with 100,000 detectors on ground. Space measurements are the only way to access the lowest multiples with great precision. Since both B-mode bumps, reionization bump and recombination bump, need to be observed for the firm confirmation of cosmic inflation, we need measurements from space. We also have great complementarity with ground-based CMB projects. Foreground information from space will help foreground cleaning for ground CMB data, whereas high multiple information from ground will help D-lens space CMB data. So our vision for 2020 is thus to have a small, relatively small aperture satellite focusing on low L measurements and large aperture ground-based telescopes as a powerful duo. And actually, I've been advocating this vision in last 10 years, and probably I'm not the only one, but I'm very happy now that LiteBIRD is selected and Simons Observatory is funded and in preparation, and CMB S4 is gaining momentum. Okay, as for the operation, LiteBIRD will take on the L2 Lissajous orbit. With our scan strategy, the satellite looks like a spinning top, a bit like this. The spin axis has an angle of 45 degrees with respect to the anti-sun axis. And the both side vector has an angle of 50 degrees with respect to the spin axis, with a spin rate of 0.05 RPM, which is rather slow, but thanks to the halfway plate rotation, this is not a problem. And the precession time of about, say, in this case, 3 hours. You got this trajectory in one turn in 3 hours, one precession, so to speak. And then in one day, you have this nice disk. And in 1 week, that disk is moving slowly. And in 1 month, you look like that. You look like the heat map like this. And then in 6 months, you cover the entire sky. And in 1 year, you have a pretty good uniformity. And thanks to this specific, the scan strategy, you have a very nice attack angle variation, which is very important for us to mitigate systematic uncertainties, instrument systematic uncertainties for polarization measurement. So this scan strategy is rather different from what Planck adopted. Now, foreground cleaning, there are a bunch of experts in the room. I'm not sure if I should say that in the room, but in this Zoom conference. So probably I'll be just brief on that. But this, of course, one of the central themes of this workshop. So for our studies during so-called pre-phase A2, we adopted the methodology described in this paper by Joskin, Erard, and Radek Stampor. And one of the keys is that we took spatial variations into account as much as possible. And then we result in, as written here, 6,144 parameters. And with this so-called multi-patch technique, we obtain the error on R of 0.6 times 10 to minus 3, which satisfies our requirement with negligibly small bias. And importantly, we also got the consistent results from Commander 2. Now, actually, now that this result is more than 1 year old, and then experts have been making a great effort. So, and then for further improvements, which I do not show today, but to me, the method is promising. Talking about systematic uncertainties, and which is also coupled to calibration strategy. we adopt a kind of systematic approach for systematic uncertainties. And we start from listing sources of systematic uncertainties and identified in our pre-phase A2 studies, 70 items in 14 categories. And for each item, we allocate 1% of total budget. We then define our method to estimate uncertainties, including some assumptions on the calibration methods. In case you find some outstanding ones, we allocate special budget. And then to obtain the final results, we make a sum on the map base and then obtain the sigma R. So I'm just describing our strategy, and then we iterate this procedure by adjusting error budget allocations. And then at the end of the day, you achieve the best result, and then I don't have time to go into each source, but as an example, here I show studies of systematic errors due to halfway plate imperfection, because this halfway plate based polarization modulator is a unique one. And then, which was of course not used for Planck. So the realistic halfway plate has some imperfection and has some frequency dependence and incident angle dependence. So we went through some simulation. Muller matrix based model was made based on this RCA-WA simulation. At the end of the day, I mean, ultimately, we will confirm the validity of that with measurements, but for now, it's a simulation. And then we obtained the leakage maps, and then we estimated the sigma R coming from that. And then the right figure shows the result. So in this sort of way, now all non-systematics are addressed. But of course, we are continuing the effort. And one thing we are really focusing on is real next step, which is a combination of the foreground cleaning and systematics. And although I don't have much time to go into detail for that, one example we recently published is the bandpass uncertainty coupled to the foreground cleaning. And then we derived some requirements on the bandpass measurements in our ground campaign, which is one of the very important pieces of information for our development. Okay, so one nice thing about LiteBIRD is that the mission requirements are very simple. Hence, system requirements are derived from that very simple mission requirements. Having said that, once we have very nice measurements, then you can think of a variety of science outcomes. And then I don't have, again, time to go into every detail, but we are very active in pursuing these themes. And then I'm going to show a couple of examples here. But one thing I do not show anything today is, for example, galactic science. We recently formed a new galactic science group or activities inside LiteBIRD. So, and then it's already, the studies are already very interesting. So I hope that in the near future, we can start sharing such information. So as I said already, system requirements coming from this full success. And then in principle, these additional science outcomes are sort of quote unquote guaranteed if full success is achieved. And then this is not exactly included, so that's why I call extra success, we can think of further improving our R measurement by using external pieces of information. Note that our full success, when we talk about full success, we don't even rely on delensing. So that full success is done without delensing. That's a very important point you need to remember. And then the extra success could be made by using external pieces of information, and then that seems to give us further, improvement, which will play a very important role. And we will be able to measure the E mode very precisely, and that cosmic variance limited measurement of EE will be very important and guaranteed legacy for LiteBIRD, and that will give us this cosmic variance limited tau measurement, and then that will shed light on the reionization history, and that will be also useful to mitigate the parameter degeneracy, and then that gives you improved determination of the some of the neutrino masses together with the other measurements, of course. So this is an important addition. Now, let me just touch on a little bit more about the mission instrument. There are three important features of our mission instrument. One, as I said already, there are two sets of telescope with TS arrays. And then secondly, a polarization modulator with rotating half-wave plate for 1/f noise and systematic reduction. And thirdly, cryogenic system for 0.1 Kelvin base temperature. So the low frequency telescope has this reflective mirrors, and the MHFT consists of two refractive telescopes with this sort of TS arrays, and this gives you the sensitivities for each band. So having 15 bands in the staggered configuration like this is a very powerful way to keep enough number of bands and then keep some robustness. And as I said, this polarization modulator with the rotating half-wave plate, this will upconvert your signal, and then in that way you can much reduce the 1/f noise. And the cryogenic system consists of, well, this is a kind of all-star cast because several agencies are involved. So this is a very powerful cooling chain that we plan to adopt. Now, okay, so the technology development in Japan, this is just to demonstrate that we have three major institutions: JAXA, KEK, which is an accelerator lab, but it has this CMB group, in the cavity IPMU. So we are very active in the current round of the R&D. And this is an example of such R&D. This is achieved by the cavity IPMU group, the first time in the world. This very large LFT polarization modulator demonstration. Now, one of the most important things to me, and this is a strength of LiteBIRD, is this very powerful joint study group with more than 200 researchers. Actually, now I should say more than 250 researchers from Japan, North America, and Europe. And the team has a lot of experience of course, in CMB experiments, but also some people are from X-ray satellites and also from other large projects, including ALMA and high energy physics. Oh, so this is international task sharing, and probably I don't go into detail because I have each slide describing each region's activity. So US LiteBIRD program has these deliverables. Basically, simply put, they are in charge of cold system below 4 Kelvin. And they are the group at UC Berkeley led by Adrian Lee is very good at producing very nice superconducting detectors, I mean TS bolometers. So they are developing the space-grade TS bolometers right now. And one thing I want to add is that this ground-based project has a nice link to LiteBIRD. Indeed, this Simon's Array project in Atacama, Chile, can be regarded as a prototype of LiteBIRD in many senses because it uses basically the same TS bolometer technology, same cold readout technology, and warm readout technology. So this will give us very important pieces of information, lessons learned, is serve as an important field test of detector and readout technology LiteBIRD plans to adopt. And here's a summary of funded Canadian LiteBIRD activities. They are very good at producing warm, electronics, readout electronics. So this team is led by McGill University. But of course, they are also strong in data analysis. So they are now involved in systematic error studies. So, and one thing is that now recently they agreed to work with the Italian group under INFN. So they are building a nice international team for this warm readout system. Now, last but not least, the LiteBIRD European Consortium. It's really a strong LiteBIRD participation from Europe. Now, CNES committed to phase A, ASI committed to phase A, and Spain also committed to phase A. Other national agencies and ESA are under discussion. So Europe is in charge of MHFD and ADR, and this activity is led by CNES. And indeed, about 50% of LiteBIRD Joint Study Group members right now belong to European Consortium. So I'm almost ending. And then just one news is that we plan to update some of the design information at SPIE 2020, which will be held in December, about 4 weeks from now. And also, we also plan to submit a comprehensive overview of LiteBIRD to Progress in Theoretical and Experimental Physics journal, PTEP, in the near future. So stay tuned. So this is the last slide. LiteBIRD is selected for JAXA's L-class mission number 2 with the expected launch in this decade. Observations for 3 years around Sun-Earth Lagrangian point L2 will be carried out to have this millimeter wave all sky surveys with 15 bands between 34 to 448 gigahertz. So the full success is to achieve delta R better than 1.10⁻³ and indeed foreground cleaning studies indicate this could be even better. And we have a very thorough systematic error studies, but we are going beyond that already. So I hope that in the near future, we will show you some more new, more advanced results from LiteBIRD. And it's the group itself is growing, and then it's really important. It's been really important thing that the great success of Planck gave us a lot of lessons learned, and that should be adapted to LiteBIRD in a proper way. So so that's final word from me. So I stop here. Thanks a lot.
Thank you very much, Masashi.